But now let's get into the online PD on switchgear. So if we're looking at medium voltage air insulated switchgear, typically the type of defects we might find inside our air insulated switchgear, so traditionally again 11 kV, 33 kV range of switchgear, typically causes of PD could be voids inside solid insulation or air inside liquid insulation. So if you've got a compound filled cable termination, or if we've got a solid piece of insulation with a void inside, that's where we can find PD. Could be a crack on the solid insulation, so maybe that's damaged during installation, maybe that's damage from the factory, so you could get a physical crack on that. Number three, you could get air gaps between conductors. So the most common area to find that is maybe on the rose connector, where the circuit breaker meets the pin in the actual switchgear. Quite often, if that pin's damaged in any way, you might get an air gap between those two, and therefore you can get partial discharge occurring between that air gap. And or contamination or heightened stress on the surface of termination. Now, there is a slide dedicated to cable termination PD, so I'm not going to go through that in too much detail at the moment. But for these first three, the voids inside solid insulation, cracks on solid insulation, and the air gaps between conductors, the most common sensor to use to detect these PDs are TEV sensors, TEV sensors. And basically these TEV sensors, TEV stands for transient earth voltage. It's a name given to the signal that's generated from these PDs. And these TEV sensors are optimized to pick up PD that's occurring inside the medium voltage air insulated switchgear. So if we've got a discharge occurring inside the switchgear on an air insulated, what will happen is when the PD occurs, we would get a very high frequency signal that's emitted from the PD point. It's induced on the inside of the switchgear panels, depending on which component is discharging. Of course, it can be occurring anywhere. Depending on which component, depends on which compartment the signal is induced. Signal will induce on the inside of the compartments, travel out through the gaps between two panels, so where two panels meet. And of course, this signal is a high frequency signal, and so it's going to follow high frequency characteristics. Going to travel across the inner surface of switchgear, out through the gaps in the panels, and then a TEV sensor is attached to the outside of air insulated switchgear, and basically it's a capacitive sensor. So when this high frequency signal travels across the surface of the sensor, then we can detect PD. PD is induced on the sensor. Now, TEV sensors typically are from 3 megahertz to 80 megahertz, though they can vary. And in fact, our handheld instruments operate at much higher frequency in the TEV range. But typically, we're looking at 3 to 80 megahertz, especially for a sensor that might be attached to a monitoring system, because we've got to consider the effect of the high frequency signal on the cable run as well. And so yeah, two types, either built in. So if it's a handheld instrument, typically the TEV sensors are built into the head of the equipment. Or if it's a sensor, then typically it's an independent sensor, a bit like this, that might be connected to a monitoring system. So if I just show my little animation there. So PD would come out through the gaps in the panels, travel across the surface of the equipment, and be induced or detected by the capacitively coupled sensor on the outer switchgear. So just a reminder, PD inside air insulated switchgear, also known as internal PD in this slide example, could be voids inside solid insulation, cracks on the solid insulation, or air gaps between damaged conductors. PD occurs induced inside compartments and then travels across the outer surface. And then typically medium voltage air insulated switchgear for internal PD, typically we're using TEV sensors, transient earth voltage sensors. Okay, so next one I'm going to look at is gas insulated switchgear. And for a very specific reason, I've jumped straight up to EHV GIS. EHV, gas insulated switchgear, is a very common type of PD test that's conducted. It's very familiar to a lot of people, which is why I've jumped onto that before looking at medium voltage GIS, if you like. So EHV GIS, this is typically on my version of a GIS compartment. So here we've got a insulation band between two components, two compartments of the equipment. And inside, this is what it looks like. So this is inside our GIS. So if you excuse me, this line has managed to find its way somewhere. So the types of PD we might find with inside EHV gas insulated switchgear, we might find free moving or floating particles. We might find a protrusion or a particle on the housing. So this is coming from the outer housing of the tube, if you like. There might be a protrusion pointing inside. We might find a protrusion on the conductor or even a particle on the conductor as well. We might find a particle or defect on the insulator. So on the outer surface of the insulating point, we might find a particle on that. Or we might find a defect within the insulator. So that could be a void, a bit like similar to I mentioned on any insulator, of course, can have a void or a defect inside, or it could be a delamination. So where the insulator is not quite making firm contact with the conductor. So for GIS, we use a few different types of sensors. UHF sensors are typically what's used because EHV GIS is sealed. It means that most lower frequency component signals, so typical signals that would be in the frequency of, say, TEV sensors, like the previous sensor I mentioned, the lower frequency signals will struggle to escape from the GIS switchgear. And so it's only on the UHF level, the ultra high frequency level, where the signals are able to escape. And typically they escape through the barriers here, in which case we would use barrier sensors. So if there's barriers that we can attach an external, what's known as often known as a barrier UHF sensor, we would attach that. A window sensor, so more modern GIS equipment may have a window installed, which of course is still sealed in terms of keeping the gas inside the chamber, but has the ability to apply a UHF sensor, and it's a UHF window. So UHF signals will still be able to escape through that window. Also, more modern GIS equipment has pre-embedded or pre-installed UHF sensors. So EHV GIS, the sensors that are used are UHF sensors. Typical frequency range between 200 megahertz to 2.5 gigahertz. And then there's three types of sensors that are generally applied: barrier sensors, window sensors, or existing internal sensors. Now, in terms of the equipment you would connect that to, similar to the TEV sensor, the previous example I used, you may connect that to a permanent monitoring system. You may connect these sensors to a portable equipment, depending on the actual PD equipment that you'll be using. In IPEC's case, we manufacture both types. So we can connect these sensors to our permanent equipment, or we can connect these sensors to our portable handheld equipment as well. Okay, so now I'm looking at medium voltage gas insulated switchgear. So the reason I used the EHV level first is because I wanted you guys to have an understanding of GIS on the EHV before mentioning GIS on the medium voltage. And because they're very different pieces of equipment. So GIS on medium voltage is a bit trickier than on the EHV. So on the EHV level, we can install our UHF on this barrier, and this answers one of the questions here. Because the barrier sensor is external, no outage is required. So we can install UHF sensor on the outer barrier, no outage is required. When we're looking at GIS, the problem on medium voltage, the problem is they're much squarer. They don't have these gaskets where you can install the sensors. And so typically, there's no point at which you can easily install a UHF sensor. Equally, it's not common practice for switchgear manufacturers to have UHF windows on medium voltage. It's not common practice for switchgear manufacturers to have pre-installed sensors on medium voltage switchgear. And if you guys run power networks, please lobby your switchgear manufacturers, because that would be a fantastic case. And so what happens is on GIS, as the PD occurs, the PD will be trapped and remain inside the gas compartment and cannot escape, because this is sealed. So unlike air insulated switchgear, where the PD will come out through the gaps in the panels, this is sealed, and therefore it cannot come out. However, there is a few points on the medium voltage network where PD can maybe occur. So in this case, for example, quite often PD can escape through the gasket where the cable terminates inside the GIS. So PD cannot escape in all locations because the panels are sealed, but it can escape from some gaskets or cable entry glands. However, you need to have caution when looking at PD on medium voltage. So although we can use the TV sensors, we need to consider that the PD may have traveled quite a long way and it might have attenuated before being detected by the sensor. So equally, the sensor location, so where you're placing the sensor on the GIS, is quite applicable. So if a PD is occurring on a medium voltage air insulated switchgear, typically what would happen is the PD would escape through any gap, because there's lots of air gaps between panels, and travel maybe 4 or 5 meters along the outer surface of medium voltage switchgear. In the case of GIS, the PD may have already traveled many meters before it's found an exit point. And so when you're detecting the PD, it might be of a much lower value than it would be on an equivalent air insulated switchgear. So when conducting tests with TV on medium voltage gas insulated switchgear, we just need to carefully consider the level at which we're detecting the PD. Generally, what I say, if we detect any PD on gas insulated switchgear, we cannot judge the value. So on air insulated switchgear, we can use that dB level as a judgment of whether the PD is minor or severe. On a gas insulated switchgear, we cannot. If we detect PD, that's great, but we cannot judge whether that PD is actually low, medium, or high because we do not know how far that PD has traveled before it's escaped. So bear in mind where we're placing the sensors and bear in mind how we're doing the test. Okay, so now I'll move on to PD and cable terminations then. So cable terminations in our switchgear, we may have more commonly surface tracking is occurring. So it's contamination on the surface of insulators. So maybe that's a buildup of dirt, buildup of grime, a buildup of dust. Or a heightened stress due to incorrect termination. And in fact, these two pictures are an example of the heightened stress. So we can see in these two cases, these stress cones are touching, these phases are a little bit too close together. So this is a typical surface tracking activity occurring here. And again, this picture at the bottom, 2 phases where the insulation has been stripped back a little bit too early, and then the 2 phases are still close together. And so naturally, these are not correctly insulated, and so we get this discharge, this pitting occurring between these 2 phases. So basically what happens is the best type of sensor to use for cable terminations are generally ultrasonic sensors. They're relatively simple. They're 40 kilohertz microphones, very, very simple sensors, but they're very, very sensitive. So while some switchgear is sealed and they can't always be applied, particularly for spot testing, maybe permanent monitoring, we can install the sensors inside terminations. That's quite a common thing to do, like this sensor here. Install inside terminations. For portable handheld equipment, some switchgear is sealed. However, some switchgear, you have louvres or you have gaps in the panels where you can maybe get audible or ultrasonic signals coming out. And so all we need to do is point our ultrasonic sensor in the direction of the HV point. The directional sensors, about a 30-degree window. And if the PD is occurring, then it will be detected by the handheld instrument. So ultrasonic sensors, like I said, very simple. They're just microphones. They're very, very sensitive. So at the very early stages, before PD is visual inside cable terminations, before you can see PD, you will be able to detect it with an ultrasonic sensor. 2 forms, either permanent monitoring type of ultrasonic sensors or handheld type of ultrasonic sensors for cable terminations. In outdoor switchyards then, so ultrasonic sensors are also used on outdoor switchyards. So it's basically anywhere where we have bushings occurring, anywhere where we might have partial discharge occurring across the surface. Then basically what we can use is a parabolic dish. So parabolic dish used typically extends the range by 20 to 30 meters. So 20 to 30 meters is extended. And then we can see we can see surface tracking activity. So they can come with lasers, they can come with sights. So basically what you do is you can point the ultrasonic sensor with a parabolic dish extending the range by 20 or 30 meters over to the HV points so that you can see the discharge occurring remotely. Now, the only warning I would say, so the type of activity you may find on this type of equipment is contamination of the insulator or ionization of the air due to corona. Now, corona typically, although it will look like PD, typically it's not so damaging because the air is being ionized. It's not actually, and it's from a conductor. It's not actually damaging an insulation over time. So one thing to consider when using a parabolic dish and outdoor switchyards is using the ability, the directional capability of this equipment, and then moving it up and down the insulator points so that you can and moving around, physically moving around your switchyard so that you can decide if the PD is occurring across the surface or the PD is a corona occurring from ionization of the switchyard. And again, switchyards exactly the same as those medium voltage pole mounted cables and the associated bushings there. So as well as switchyards, you can use it on transformer, open transformer bushings, or you can use it on the overhead line connections as well. Okay, then finally PD detection with other types of sensors. So of course we all know that something like a HFCT is primarily used and generally used for detecting PD in underground cables. However, HFCTs can also detect PD in switchgear. So a normal HFCT would have or rather the IPEC specification HFCTs. Our standard HFCT, 60 kilohertz to 80 megahertz. But we do have some dedicated switchgear focused HFCTs. So you can install a HFCT in exactly the same way you would for cable PD, attaching it on the earth sheath or around the core. But it has much higher frequency response. So 1.3 megahertz up to 360 megahertz is one of our HFCT focused on switchgear. And this higher frequency component of our HFCT means it will also be able to detect PD coming from within the associated switchgear. So that could be medium voltage AIS, medium voltage GIS, or even in some cases, the EHV GIS. Although, like I said, we do need to consider that even 360 megahertz is on the lower end of the UHF sensors. So for sure, for cable terminations on GIS, EHV GIS, it's best to use the UHF sensors. But HFCT systems can be used to detect PD on switchgear as well. And in fact, IPEC's monitoring system, IPEC's test equipment, use this functionality, and HFCTs will also plot and track PD in switchgear. UHF-E, though the E stands for embedded, so we have another type of UHF sensor that's not focused on EHV GIS. Our UHF-E sensor is focused on the medium voltage equipment. So typically the application here is inside cable terminations. So like I mentioned, you can install the ultrasonic sensor inside a cable termination. That's going to be focused on surface tracking activity. However, if you have defects inside the insulation of a cable in a termination, for example, it will emit a high frequency signal that could be detected by the UHF sensor. And so installing a embedded UHF, so typically it's applications where we would also install a ultrasonic sensor. We take that opportunity to install an embedded UHF sensor inside the cable termination so that if PD is occurring inside that termination that's not visible on the outside for an ultrasonic sensor, then this UHF-E sensor will be able to detect this PD activity. So UHF-E is designed for PD detection in cable terminations, internal PD inside the cable insulation itself, and again, it's an ultra high frequency sensor. So in cable termination, PD would generally be detected by this UHF before being detected by a TV sensor. So to summarize the application of different sensors, and of course there is unique cases where depending on the equipment type, we would look to apply different sensors. So what IPEC do is on each individual case of either a certain type of switchgear, a certain type of voltage level, a certain type of concern from the customer, we would match the sensor to the requirement. However, typically on medium voltage air insulated switchgear, we would use TEV sensors. On medium voltage gas insulated switchgear, we would use TEV sensors. On EHV gas insulated switchgear, we would use UHF sensors. On cable terminations, so cable terminations for the medium voltage, we would be looking at ultrasonic sensors. And on outdoor switchyards or outdoor overhead line insulators, etc., then the parabolic dish, which is an ultrasonic sensor, the parabolic dish would be used. Sensors themselves are detection devices. They're optimized for detection of PD in the different types of assets types, in the different types of how PD can occur. They will also pick up background noise, and they will also pick up external interference sources. And so it's important to consider not just the sensor type. So having a TEV sensor, having a UHF sensor will not mean you're able to detect PD. It's important to consider what you're connecting these devices to in order to detect the PD activity. There's multiple partial discharge devices out on the market. They all have different advantages and disadvantages, and they all handle that data processing in a different way. It's important to connect these sensors to a device that is effective at differentiating PD from background noise, so you can actually detect the PD signals. It's not good enough just using these sensors.